Hey everybody, this next video lesson is going to cover the concepts of volatility and vapor pressure. First, we'll talk about what is volatility. Well, you've probably heard of this term before, and it probably has to do with something that's unstable. Maybe even somebody is known as a volatile personality. They maybe get angry really fast or change emotions quickly. But in volatility, when it comes to chemistry, has to do with evaporation, or at least escaping to gas. Sometimes it's liquid to gas, which we learned in a previous video lesson, which is known as vaporization, but it also could be solid to gas, which we call sublimation. As long as the conversation revolves around converting to a gas, then we're talking about volatility. Now, as you probably have experienced in your everyday situations, volatility is closely dependent on the temperature. On a warm day, evaporation happens faster, and on a cool day, evaporation happens not quite as fast. But we'll talk a little bit more about what's happening on the molecular level when it comes to volatility. Besides temperature, volatility is also very much dependent on the strength of the intermolecular forces of the substance or substances that you're looking at. Things that have high or strong intermolecular forces are low volatility. Intermolecular forces are what keeps solids solid and what keep liquids liquid. Without intermolecular forces, all matter would be gas. So as you increase the intermolecular forces while keeping the temperature constant, you are more likely to have a liquid or a solid and thus decrease the volatility. Let's take a look over here at this graph, and you might recognize this as a Maxwell distribution from our gas laws chapter, and you'd be correct. But this concept can also be applied to things like evaporation, volatility, and vapor pressure and things like that we're about to discuss. Once again, the peak represents the number of molecules that are at that particular kinetic energy. So as kinetic energy increases on the bottom and number of molecules of the substance goes up as you go up the left-hand side. And at low temperatures, the distribution of kinetic energy of those particles is represented by a high peak that goes up quickly and comes down quickly. Both of the red and blue line represent the same substance at different temperatures, as you can see labeled on the graph. As the temperature increases, all of those particles spread out their kinetic energy to a wider range, but they all are conserved. What you'll see is that the peak shifts down and to the right as temperature gets higher. We may have a lower number of particles traveling the average kinetic energy, but overall, we have more particles traveling a higher energy as you get out closer to the right side of this bell curve distribution of kinetic energies for these particles. In order for a substance to be volatile, the particles of that substance need to reach a minimum kinetic energy threshold in order to escape from either liquid to gas or even from solid straight to gas. And if that minimum energy threshold isn't met, then the particles will not change state of matter. They will stay in the state of matter, the more organized state of matter that they are. But not all particles are traveling the same speed, as we can see by the Maxwell distribution here. So a handful of particles that are traveling at kinetic energies high enough to achieve volatile state, a state that would represent them being able to escape to a gas, those particles will be able to be given off as a gas and are no longer part of the solid or the liquid that the state of matter is representing at that current temperature. And this graph does a really good job of explaining why at higher temperatures more particles evaporate compared to lower temperatures. Consider a puddle on the street, say maybe right in front of your house in a cool spring morning. The temperature of the puddle is pretty low, but as the temperature warms up in the day, the evaporation of that puddle becomes more likely. And you might think, well, that's just because, it's warmer. But why? Why is it evaporating at a higher temperature? You have more particles, as you can see, the difference between the red shaded region and the blue shaded region. You have more particles that have that minimum kinetic energy needed to escape back. So as you heat the temperature of the substance up, you shift the peak down and to the right, but you also make it wider at the base. And that wider at the base concept allows for more particles to reach the minimum kinetic energy threshold compared to the blue particles. If the temperature stayed cool all day, we would get some evaporation, but not as much as if you increase the temperature as the sun gets higher in the sky. And on warmer days, you get more escaping particles due to evaporation. It's important to note that the minimum kinetic energy line doesn't ever really change when you change the temperature of the substances. It's the distribution of the particle speeds that change, and you just simply have more particles achieving that minimum kinetic energy. Some people think that as you increase the temperature, this line actually gets closer or lower, less kinetic energy needed to escape to gas. But that's not true. You are shifting the peak, not the minimum kinetic energy. Furthermore, substances that are more volatile, now you're shifting the actual dotted line. If you have a substance that's more volatile, let's just say maybe this line represents the minimum kinetic energy for, say, water. Now, if you were comparing that to something that is more volatile, like maybe, say, ethyl alcohol, it's polar, but not quite as polar as water. And so, since it's less polar, it is more volatile. And its dotted line that represents the minimum kinetic energy needed to escape would shift a little bit further to the left. The more volatile substance is, the less minimum kinetic energy needed to escape. And a substance that's more stable or has stronger intermolecular forces would shift the minimum kinetic energy down to the right, meaning that you need to increase the temperature much higher in order to start to initiate evaporation, because the particles in the speed distribution will be close to zero before you can reach that line of volatility line. We'll call it the minimum kinetic energy line. So you need to shift this peak way far to the right. Now it's going to get lower, but it's also going to shift further to the right. And only once you reach those higher temperatures will you have enough particles to be able to cross that line and achieve a volatile state or escape into a gas. I suggest you check out page 443 in the textbook for some supplemental reading on the concepts of volatility. Now let's talk about vapor pressure. Now I've introduced you the concept of vapor pressure back in the gas laws unit, but now we're going to talk about the reasons why pressure of a vapor exists and tie it closely to volatility, and talk about the connection between volatility and vapor pressure. Vapor pressure is identified by the P subscript VAP for vapor. What is vapor pressure? Well, it's the pressure of an evaporated gas inside a container. So it has to first start out as a liquid, then the liquid has to evaporate into a sealed container, and the pressure of that evaporated gas results in vapor pressure. This picture on the right shows you exactly what's happening. At first, the pressure is zero inside the evacuated flask because there's no liquid inside and there's no particles. All the liquid is held up here. This is liquid ethanol. So we're going to let a portion of the liquid ethanol into the chamber. And at first, the particles are going to be starting to escape. There'll be very few particles that are escaping, and so the vapor pressure will slowly build over time. Eventually, you'll get to a point where you have the same amount of particles escaping as you do reconverting to liquid. And that system reaches dynamic equilibrium, a concept that we will talk about at greater depth in the upcoming months. But you have escaping particles to gas and gas being captured as liquid at equal rates. And so you've reached a pressure equilibrium. Now, the pressure that gas is exerting on the container is known as vapor pressure, or PVAP. I'd also like to point out that vapor pressure is a characteristic of the liquid, not the actual gas itself. Now, I realize that pressure is a property of gas, and vapor itself is talking about gas, but vapor pressure is a property of the liquid. Now, as we discussed back in the gas law units, the vapor pressure of a liquid is strongly dependent on the temperature. And as you witnessed and as you saw back in that chapter, as the temperature of the liquid goes up, the vapor pressure goes up. But why? Well, the reason why, as we learned on the last slide, is that as temperature goes up, you have more particles that are able to reach that minimum temperature or that minimum kinetic energy to escape to gas. So you have increased volatility. So the more volatile the liquid, the more pressure is going to be over the top of that liquid because you have more particles escaping from liquid to gas. But as we talked about also in the last slide, volatility isn't just dependent on temperature, it's also dependent on the intermolecular forces. If you have something that has low intermolecular forces, well, then it's going to be extremely volatile. And high volatility, once again, results in a higher vapor pressure. So if you're comparing two liquids and you're asked, if you keep the temperature constant, Which of these two has a higher vapor pressure? Well, really what you're asking is which one is more volatile. The one with stronger intermolecular forces will be less volatile and have a lower vapor pressure, whereas something with low intermolecular forces has high volatility and a high vapor pressure. So if you're comparing two liquids and you may not know the actual values of the vapor pressure, you could make a very good judgment based on the polarity and the strength of the intermolecular forces of those substances. Now, the last thing I want to talk about in this video lesson is the role that vapor pressure plays in boiling points of different liquids. And eventually, I'll get over to this table here in the lower right-hand corner. But first, let's talk about boiling liquids. And let's also take a look at the forces that are involved in the concept of boiling liquids. Here I've drawn a couple of beakers. Let's first focus on the one at 20 degrees Celsius. We'll talk about the one at 100 degrees Celsius here shortly. So this is room temperature. Now at 20 degrees Celsius, water has a vapor pressure, which means that some of the particles are escaping to form gases. Now the other force that's involved here is the atmospheric pressure, because as you know, we boil water. Maybe we're making some macaroni and cheese on the stove. That's always my go-to example. But there's always an opposing force. The pressure of the liquid is escaping at 20 degrees Celsius, but there's an atmospheric pressure, a very large one in comparison, that's actually pushing back down against the liquid. And so these two opposing forces are basically working against each other. And because the atmospheric pressure is very, very high compared to the vapor pressure of the liquid, then for the most part, the liquid stays in the liquid state of matter. Maybe a couple of particles escape because it has enough energy to escape to vapor, but the atmospheric pressure is keeping the liquid water from boiling vigorously. Now, as we pointed out earlier, if you increase the temperature of the liquid, the vapor pressure begins to increase. And so let's crank up the temperature to near 100 degrees Celsius. And at that point, the vapor pressure, which I'll label with this blue vector, is pretty large compared to 20 degrees Celsius. So we have a stronger evaporation. We have a stronger vapor pressure that is basically trying to cause the liquid particles to escape and push out on the atmospheric pressure. That is still present over the top. Now, the atmospheric pressure doesn't change necessarily because the amount of gas over the top of the liquid remains about the same. Vapor pressure has increased with an increase in temperature, but the atmospheric pressure has stayed the same. But now you get a situation where the atmospheric pressure is equal to the vapor pressure, and at 100 degrees Celsius, the vapor pressure of the liquid is large enough to be equal to the atmospheric pressure, and now what we witness is a vigorous boil. People often think that boiling has to do with the temperature, but really, the temperature is causing an increase in vapor pressure, and it's only when the vapor pressure is equal to the atmospheric pressure do we see boiling. Boiling is no longer a cause from temperature. Boiling is caused by pressure. Hey everybody, welcome to my basement laboratory. As you can see, we're in the office. But we were talking about boiling point. Boiling point is when you increase the temperature of the water high enough that the vapor pressure equals the atmospheric pressure. Another way to boil water is to reduce the atmospheric pressure. I've got water in this syringe. The water is pretty cold. It's right out of the tap. And I've sealed this syringe with a bit of hot glue. Now if I can reduce the pressure so that it is equal to the vapor pressure of the water inside, I can make the water boil at very cold temperatures. So all I need to do is reduce the pressure by lowering the plunger, and you can see the bubbles start to form there. Now you might think, oh, Mr. Cohn, you're just sucking air in. But remember, the opening is at the top. I'm not sucking air bubbles in. The bubbles are forming at the bottom, and they're bubbling up like boiling water. So if I can increase the temperature, I can cause the water to boil, or I can decrease the pressure over the top of the water so that the vapor pressure equals the atmospheric pressure. Atmospheric pressure. It's not magic. It's chemistry. Down here in the lower right-hand corner is a graph of temperature versus vapor pressure of 4 different substances. You got diethyl ether, which is a fairly nonpolar molecule. You got ethyl alcohol, which is slightly more polar, water, which you know is very polar, and ethylene glycol, which is more polar than even water. If you look at the temperature increasing, you'll see that the vapor pressure begins to increase of the liquid and starts to increase very much at the end. Notice the dotted line, which represents the normal boiling point of a particular liquid, is based on the pressure, not the temperature. And so 760 torr, which is equivalent to 1 atmosphere of pressure. Eventually, water gets warm enough where its vapor pressure equals 1 atmospheric pressure, and that is at 100 degrees Celsius. But ethylene glycol would cross the boiling line at a much higher temperature, one that we can't even see off the screen. Now, ethyl alcohol we can judge as less polar than water because its normal boiling point is 78.3 degrees Celsius, and so its vapor pressure equals the atmospheric pressure at 78.3 degrees rather than 100 degrees. So as you move to the left, these substances become less polar or weaker in their intermolecular forces. And as you move to the right, or as the boiling temperature increases, that means that you have stronger intermolecular forces because the boiling point temperature is much higher than that of water. Well, that takes care of this video lesson on volatility and vapor pressure. Thanks for watching.